Precalculus Lesson 20, Applications of Exponential and Logarithmic Functions, continues with exponential decay. This is from section 4.5 in the college algebra textbook. We return to the formula for exponential growth or decay, which is a of t equals a naught e raised to the kt, noting that the formulas for growth and decay are the same. The only difference is that now for decay, k will be less than 0. So our constant k is negative if we have exponential decay. And then let's look at the half-life of a radioactive substance before we start solving problems here. The half-life is the time required for half of a radioactive substance to decay. If you think of having two healthy teeth, how long does it take for half of those two healthy teeth to decay? That would be the half-life. Our first problem here, an unknown radioactive element is found to have a half-life of 1,740 days. How long will it take for a sample of 100 milligrams to decay to 87 milligrams? And just like with exponential growth, the first thing, if we don't know what our constant k is, that's the very first thing we have to find. And in this particular problem, we don't know what k is. What we can use here is our half-life, and we'll do that. We use the formula a equals a naught e raised to the kt. And the way we use the half-life is we note that at the half-life, 1/2 of our original amount of substance remains. And so we can set a equal to 1/2 a naught. And then we also note that happens in this problem at the time t equals 1,740. So we set t equal to 1,740 and continue to solve the equation, first of all, by dividing through by a naught to give us 1/2 equals e raised to the 1740k, then taking the natural log of each side of the equation. And if we realize on the right side, the natural log of e raised to the 1740k is equivalent to 1740k, we've simplified our equation to natural log of 0.5 equals 1740k, from which point we would divide both sides by 1740 to get k equals the natural log of 0.5 over 1740. And as before, I don't want to put k into a calculator. I don't want to approximate k. I want to keep it exact until the end of my solution process to avoid rounding errors. So let's move on to now actually finding how long it will take for this sample to decay. And so I'm finding t here, the time. What I know here is that for my formula a equals a naught e raised to the kt, using k equals the natural log of 0.5 over 1740, I start with an amount of 100 milligrams. So I replace a naught with 100 in the formula, and I decay to 87 milligrams. So I will replace a, the amount we have at time t, with 87. And also k, we're going to replace the value we found for k in the first part of this problem. Now I'll divide through by 100 to get 87 over 100 on the left side, and then proceed to take the natural log of each side of this equation. The right side at that point will simplify to the natural log of 0.5 over 1740t, and we can now solve for t by multiplying both sides of the equation by 1740 over the natural log of 0.5. We then get t equals 1740 over the natural log of 0.5 times the natural log of 87 over 100. So this is our value for t. And plugging that into a calculator, we find that t is approximately equal to 350 days. So it takes approximately 350 days for 100 milligrams of this substance to decay to 87 milligrams. Let's keep looking at this same problem setup and try to figure out how long it will take for 90% of the same unknown radioactive element to decay. And so we use A equals A naught, E raised to the KT, same value that we've been using for K. It's the same setup. And what I'm looking for here, when 90% of the substance has decayed, we're left with 10%, or we're left with 0.1 times the amount A naught that we started with. So I replace A with 0.1 A naught. I replace K with the value we found for this problem for K, and then we divide both sides by A naught to get 0.1 equals E raised to the KT. I take the natural log of each side, and realizing the natural log of E raised to the KT is the same as KT, I now have the natural log of 0.1 equals the natural log of 0.5 over 1740 times T. I multiply both sides of the equation by 1740 over the natural log of 0.5 and simplify to get T equals 1740 over the natural log of 0.5 times the natural log of 0.1, which we plug into a calculator and get an approximate value of 5,780 days, which is the time for 90% of the radioactive element to decay. Try on your own number 3. Radium-221 has a half-life of 30 seconds. How long will it take for 99% of a sample of radium-221 to decay?